All right, so we've looked a little bit at the geometry of the triple integral. The next question we want to address is, what does the triple integral actually represent? What are we finding? Well, if you recall, with a double integral, when we integrated 1, we were finding area. So what do you think we're finding when we integrate 1 with a triple integral? 1 dv now. We are indeed finding volume. V stands for volume. So we're really finding the volume of the object D. If we need to find the integral of some other function, dv, one nice interpretation is if that function itself represents the density of the solid, then we're actually finding the mass of D. This is especially interesting when we have a non-constant density, an object that's more dense in some places than others. So we can multiply each piece of density by its own little piece of volume, and therefore account for variable densities in our objects. In our next example, we're going to be taking a look at a volume problem. And I'd like to do this volume problem 3 different ways. We're going to create 3 different triple integrals that represent the same volume. We'll choose to do dx first once, dy first once, and dz first once, just to kind of help you make a little bit more explicit some of that theory that we looked at in the chart on the previous page. So we're being asked to set up but not evaluate 3 triple integrals to represent the volume of the tetrahedron in the first octant, bounded by the coordinate planes and this slanted plane, 6x plus 4y plus 3z equals 12. We need to use each variable once as the first variable of integration. All right, we won't evaluate all of them. We'll maybe just evaluate the last one to find out what the volume really is. So let me start with a little picture of what we've got going on here. This slanted plane would have an x-intercept of 2, 6x equals 12, so x would be 2. A y-intercept would be 3, and the z-intercept would be 4. So I've got this tetrahedron, this slanted plane kind of leaning into the corner, and then the little triangles in the 3 coordinate planes forming the other 3 sides of my tetrahedron. I'm going to start by saying, let's do the dz first. Let's think bottom to top. If we imagine a little column, like so, the bottom of my column is in the xy plane, which would be z equals 0, and the top of my column is in this plane. Now, just like the bottom is defined as a z equals, I'll have to define the top as a z equals as well. So if I just sort of mentally solve this equation for z, I would have 12 minus the 6x minus the 4y, and then that's all going to get divided by 3. While I'm still drawing, let's think about the region R. Since I'm doing the dz first, R is going to be in the xy plane. So that's going to be this triangle down here in the xy plane. And I'm going to draw that as well. Let's see, x had the intercept at 2 and y at 3 in the xy plane. So my region R actually looks like this. All right, our volume could then be written as the triple integral of the function 1. We're choosing to do dz first, and our z values from bottom to top go from 0 to 12 minus 6x minus 4y over 3. Thinking about the region R, I'm going to think vertical rectangles here, which would mean I'd be doing dy next. Y from the bottom to the top would go from 0 to the slanted line. That line would be y equals slope of negative 3/2 x plus a y-intercept of 3. So those are my y limits of integration. Put them on the slant here to get them in. And then finally, the dx can simply go from 0 to 2. Outer limits always constants. So that would be one triple integral that represents the volume of that tetrahedron. All right, I'm going to draw it again. Now let's choose a different setup this time. This time I'm going to choose to go from left to right. So I'm going to imagine starting over here on the left side in the xz plane. Actually, let me make that a different color, make it a little easier to see what we're doing. And I'm going to go to the right until I hit that slanted plane. So I start over here on the left at y equals 0. And I stop over here on the right when I hit the plane. I'm now going to need that plane equation solved for y. So solving for y, I'd have 12 minus 6x minus 3z divided by 4. Since I am doing dy first, that means that the region R is in the xz plane. So this time it's the triangle over here. That's my R. In the xz plane. Z-intercept is 4, and the x-intercept is 2. So there's our R. All right. Might as well get everything I need right now. I'm going to think vertical rectangles again here. So let's see, this time it would be z equals, and my slope is negative 4/2 or negative 2x plus the z-intercept of 4. Give myself a little more space this time. So my volume integral, once again I'm integrating the function 1 because I want a volume. I'm doing dy first. From the left side, y equals 0, to the right side, y equals 12 minus 6x minus 3z over 4. If I'm going vertical, that means I'm doing dz next. From the bottom, z equals 0, to the top, z equals negative 2x plus 4. And then finally dx would be going from 0 to 2 again. All right, I'm going to set this up one more way. I want to do the dx first. So once again, I'm going to sketch one more time. This time I want to think about x going from back to front. So I'm going to start back here in the yz plane, and then imagine coming forward to some little spot in the front of that plane. Since I am going to be doing dx first, I'm going to think of this back part as x equals 0. And in the front, is going to be, again, my same equation, but solved for x. So I'd have 12 minus 4y minus 3z divided by 6. Going with dx first, that means the yz plane is where the r is going to be located. And the z-intercept is 4, the y-intercept is 3. So there's r. I'm going to be boring and go with vertical rectangles again. All right, let's start setting up our volume integral. We're going to integrate 1, and we're doing dx first. So from back to front, 0 to 12 minus 4y minus 3z over 6. Since I did vertical rectangles here, that means I'm doing dz next. And let's see, bottom would be z equals 0. I need the equation of that line. Z equals a slope of negative 4/3 y plus 4. And then I'm doing dy last, and y goes from 0 to 3. All right, all three of those triple integrals should give us the exact same result if we actually work them all out, which we won't. I want to work just one of them out. As long as I'm here, I'll go ahead and do the last one, but they all represent the exact same volume, the volume of that tetrahedron. All right, we'll work the first couple of integrals by hand, and we'll use the calculator to help us with the last one. So I am just integrating 1 dx, which is just going to give me x. Evaluated between my limits of integration. Plugging in the upper limit, I'm going to get this. I'm going to take that 6 in the denominator, I'm going to pull that out front as a 1/6. And then I'm going to have the 12 minus 4y minus 3z in here. dz dy. So let's see. Integrating dz is going to give me 12z minus 4yz minus 3/2 z squared from z equals 0 to z equals negative 4/3 y plus 4. And I'm going to cheat a little bit and go on to another sheet of paper because I'm running out of space. Sorry about that. All right. So I have 1/6 times the integral from 0 to 3 of 12 times this upper z value minus 4y times the same thing minus 3/2 times the negative 4/3 y plus 4 squared. Now, that's a pretty not difficult but ugly integral. It'd take us a while to manage all of that, and I'd probably make an arithmetic mistake anyway. So I'm sure I did this one. If I could just find it here. When I plugged all of that in the calculator, if I hit all my buttons right, I actually came up with 4 for a final answer. All right. So there's one example done 3 ways. We'll come back in the next video and do a few more.